Hopefully that picks up my voice. I think it is. All right. So before we can talk about homometry, or the Z relation, first we need to know about musical set theory. So I'll give you a quick rundown of musical set theory for, again, those of you who haven't seen past lectures. So the musical scale has 12 notes in the chromatic scale: C, C sharp, D, D sharp, E, etc., etc. We can identify each of these 12 notes to a number from 0 to 11. So, oh no, my touch screen's being bad again. I'm going to draw with my mouse, I think. So we'll say 0 is equal to C, and 1 is equal to C sharp, 2 is equal to D, and etc., all the way down to 11 is equal to B. So in this way, we can kind of talk about chords or scales or sets of notes in a more mathematical sense. And this will be really helpful for when we're trying to do calculations with chords. And again, apologize for my handwriting. I am... oh, you can't hear anything? Can you hear my voice? Can anybody else hear my voice? Okay. That's good. I'm not sure what's up then with you, hexachordum. So that's how we're going to be identifying numbers to notes. So a musical set then is going to just be a collection of notes. Let's say we have C, E, and G. But instead of writing C, E, and G, we're going to just write it as numbers because that'll make things easier to deal with. So C is 0, like we said. And if you were to count up, you would see that E is equal to 4 and G is equal to 7. So this leads us to a really interesting way to think about intervals. We can just subtract one note from the other note and we'll get the interval between them. For example, G minus E, or in other words, 7 minus 4, is equal to 3. And this corresponds to the fact that there are 3 semitones between E and G. In other words, the interval of a minor third is 3 semitones. So what if we were to count up all the possible intervals that we had in a musical set? So let's do it with this major chord here. So there are 12 different kinds of intervals. There's the unisons, the minor seconds, the major seconds, etc., all the way up to the major seventh. And the octave, we're just going to consider the same as a unison. So we're going to write this out as sort of what they call an interval vector, okay? So in the first slot, we're going to have all of our unisons. So you can kind of think of a note with itself being a unison. So for example, 0 minus 0 equals 0. Because obviously C and C, the interval is just a unison or an octave. So we can count up 1, 2, 3 unisons in this chord. So we're going to put a 3 in the first spot. Now if we were to continue on, let's look for all the 1 semitone intervals. Are there any 1 semitone intervals here? I would say not. So we're just going to put a 0 here. There are no minor seconds. There's also no major seconds, right? We would have to have C and D or something like that. There is 1 minor third. We have E to G, 4 to 7, gives us 3 semitones. So we'll put a little tally there. Major thirds, we have 1 major third, C to E, so we can put a 1 there. And then fifths, well, we have, or fourths, I should say, we have 1/4, G to C. Now it's a little hard to see because, of course, C to G is a fifth, but imagine it's looping around. G to C is a fourth, so we'll put a 1 for there. And then tritones, there are no tritones, 0. And just to fill this out quickly, you'll notice that anytime we have an interval over here, it's going to be mirrored to the other side. So for example, that 1/4 we have, G to C, inverting that, mirroring it, would give us a major fifth, or a perfect fifth, I mean. So we'll put a 1 there. And similarly, we can mirror everything else. 0, 0. And we're not going to mirror the unisons because unisons, octaves, same deal. So this thing is what we're going to call the interval vector, or IV, I'll probably write for short. So if I said IV of 0, 4, 7. It's going to be equal to this guy right here. So this is pretty long. And a lot of musicians don't want it to be this long. And you'll notice we had a lot of repetition, right? All the dudes over here, like this minor third, the inversion of a minor third is a major sixth over here, right? So there's a lot of redundancy here. So a lot of people will reduce this to what we'll call the interval content. So the interval content of our major chord, we're going to get rid of the unisons because that's stupid. They're trivial. So we're going to have minor seconds, major seconds, minor thirds, major thirds, the perfect fourths, and the tritones. Now I'll note, if we had any tritones, we would divide this spot by 2, okay? So we would 1/2 this guy. And the reason for that is, let's say we had a tritone. Let's say in our chord we had C to F sharp, right? We would count this, but we would also be counting F sharp to C. So in our interval vector, we would have counted this 2 times, but we don't want that. That's redundant, so we would have divided that in half. All right, so now we have our definitions for the interval vector and the interval content. So again, I know I'm retreading a lot of ground from Jack's video, but I do want to make sure everyone's on the same page. So let's talk about transposition and inversion. So I think you'll be fine with the idea that if we were to transpose this major chord, we would have all the same intervals, right? Let's say we had the set D, F sharp, and A, the D major chord. So this in notes, or in numbers I should say, would be 2, 6, and 9. In other words, we're adding 2 semitones to each of our notes. We're adding 2 to each of our numbers. All right, and then if we were to go through, we would get the exact same interval vector and interval content, right? Because the intervals aren't changing. We just added something to all of the elements in our set. So transposition is not going to change the interval vector. Now notice too that inversion will not change the interval vector. So if we were to invert a chord, that means like flipping it upside down. So for example, the inverse of this chord here would be what would happen if we multiplied everything by -1. So pretend we had negatives on all these guys. So let's think about this. -0 is just 0 again, so that's fine. Our first note would be C. Our second note, -4, would be 4 semitones down from C, so we would have an A flat. And then 7 semitones down from C is F. So we actually get, oh no, it's not, there's some stupid dot in my way. So we would actually have an F minor triad. So we can also rewrite this like this. So we have 12 notes to the octave, so adding and subtracting by 12 gives us the same note. It's just displaced at octaves. So we can rewrite -4 as 8, because -4 plus 12 equals 8. Similarly, -7 plus 5, or -7 plus 12 equals 5. And these two chords do have the same interval vectors, because again, we're not changing anything about the structure, we're just mirroring it, we're just flipping. Yeah, so someone says they've never seen the minor 4 chord spelled like this. The order of the notes in the chord doesn't really matter. We're just thinking of them as like an abstract collection of all the notes in our chord. Hex Chord Theorem says, I'm wondering what the source is for this difference between interval vector and interval content is. Oh, so I don't know. It's really difficult. A lot of sources say interval vector and interval content is the other way around. I believe that's how David Lewin wrote it, was the other way around, but I've also read some more modern papers that write it like this. Personally, I prefer it to be written like this because I like to think of this as like the full vector, I guess, whereas this is just reducing it to like, I don't know, the content. That's just my little memorization device. But yeah, some sources you will see these reversed. Just for the purposes of this lecture, forget it and pretend that vector's the long one and content's the short one.
Just to jump in for 1 second, as someone who has read almost all of this stuff that exists, no one agrees on anything with regard to notation or how to write things. It's very frustrating, so you just kind of have to go along with whatever.
Yeah.
There's no correct way to do this. It depends on what book you read, so
absolutely.
We just have to go with it.
And some people don't even say interval vector and interval content. They just say other words. It's very annoying. But for this lecture, that's what vector is, that's what content is, and we're good to go. So let me clear the canvas. So at this point, we've established that transposition and inversion preserve the interval vector. However, sometimes two chords will have the same interval vector, but they will not be related by transposition and inversion. So this is when our idea of homometry comes into play. So sometimes you'll say it's non-trivial homometry, because I guess trivial homometry would be translation, transposition, and inversion, that sort of thing. The reason I'm going to use homometry over the Z-relation is because I personally think homometry is a more useful word. Homo means same, metry means measure, and I mean it very clearly means that two chords have the same measure, the same intervals. Also, homometry comes up in other fields such as physics and crystallography and that sort of thing, and they use the term homometry. So I'm going to not use Z-relation. I think it's kind of a meaningless word. So if we have two sets, and I'll give you a quick example that I stole from Jack's lecture. Let's say we have the sets 0, 1, 4, 6, and 0, 1, 3, 7. So try as you might, you cannot turn one of these into the other just by transposing and inverting them. However, they do have the same interval vector. Their interval content is 1, 1, 1, 1, 1, 1, 1, etc., which is really cute. They're called the all interval sets, and like I said, I stole them from Jack, so credit goes to him. But this is an interesting example. So the music theorist wants to know, when and where does this occur? Can we count them all? This is a much harder question than it sounds. So let's prove, I'm not going to prove a few theorems, but I'll give you a few theorems, and then maybe I'll show you the sources for the proofs if anybody's really math-oriented at the end. So the first interesting result is complements. So a complement of a set, let's say we have the set 0, 2, 3, 5, 6, or 5, 8, and let's say 10. I don't know. Just kind of made those numbers up. If we wanted to take the complement of this set, we would basically be taking all the elements that are not in it. So we would have 1, 4, 6, 7, 9, and 11. And of course, again, 12 is the same as 0, so we would not include 12. So what's interesting about these two complements is that they are always going to be Z-related, or homometric. So this was proved by David Lewin and Milton Babbitt. It's called the Hex Chord Theorem. So no matter what, if you have a 6-note chord, it will be homometric to its complement, which is pretty neat. However, we can generalize this a little bit further. So let's say we had, I don't know, a set A. I'm going to clear the screen. Let's say we had one set A, and its complement AC. So AC means a complement. We can figure out the interval vector of AC just from A. So let's say we had, we were looking for an interval I. So I is going to mean interval. I don't know, maybe it's 5 or maybe it's 3. We don't know what number it is, but it's some number. I don't know, how do I want to write this? I'll say M, which stands for multiplicity. In other words, the number of times that interval shows up in A complement is going to be equal to the number of times it shows up in A plus 12 minus the size of A. So let's do an example so that you can see what this means. Let's say that, and I'm going to again clear a little space here. Let's say that our set A was the major chord. Okay? So A is going to be 0, 4, and 7. Now, let's say we wanted to know how many major thirds are in A complement. So counting that would take a really long time, but using this formula, we can find it out very quickly. So we need to first find the number of major thirds in our set A, which is obviously just 1. Then we're going to add 12, and we're going to subtract, sorry, this should be 2 times the size of A. And we're going to subtract 6, since A is has 3 elements. Multiply that by 2, we get 6. And then we know that a complement will have exactly 7 major thirds, which is really convenient. Now we don't have to count it up. And you could, of course, do this for every interval and thus construct the interval vector of a complement really quickly. Okay, so that's a really important fact. Let me look at my notes real quick so I can give you next fact. If you have any questions, of course, feel free to post them in the chat, and I do check it very frequently. Okay, so next I want to talk about, let's talk about other n. So for now, we've just been looking at what we might call Z12. In other words, the set of integers between 0 and 11. And so when you get to 12, it repeats and loops, etc., etc. What if we were looking at other Zn? So, you know, maybe if you're into microtonal music, maybe you work in 31 tet or 19 tet. So you might be curious to know about homometry and maybe Z19 or Z31. So what's interesting is in Z12, we only have pairs. So, you know, you have one set that's homometric to another set that they're not the same from translation and inversion. But in Zn, we can actually have triples or quadruples or any sort of ooples. So, for example, and again, this is still kind of borrowing from Jack's lecture for now. In Z16, there is a triple. In Z24, there's an octuple. And actually in Z30, there has been found a 16-uple. I'm not really sure what the actual word for that is. If anybody knows, feel free to enlighten me, I guess. But I could not actually find a proof that, you know, infinitely large ooples, or as large oople as you want, exists. So that might be an open problem, or maybe I haven't found it yet. I'm not sure. But I think that's a pretty interesting little tidbit. But the main focus for, I don't know, the music theorist is how do we list all of them? Are there any ways that we can, you know, enumerate it? Or there a pattern that we can enumerate every single homometric set? And the answer is right now, no. However, we do have some ways to list some of the sets. So for example, we have this interesting result from physics. So let's say we were working in Zn, whatever that n may be. And let's say that we wanted to look at all the homometric sets that were 4 units long. So let's say we had A and B, and they're both 4 units. They have 4 elements, 4 notes in their set, etc. So how many homometric pairs exist, and what are they shaped like? What are the homometric sets? So let's say that n is a multiple of 13. So the way we're going to write this is 13 divides n. If 13 divides n, then we have it's blacking out because I'm switching to my notes and back, I'm sorry. If we have 13 divides n, then A and B are going to be really nice shapes. So we're going to have A is 0, n, 4n, and 6n. And B is going to be 0, 2n, 3n, and 7n. That's not a 7, that's a 7. That's really convenient. I like that. And this gives you, all the homometric pairs. That's the only pair that exists if 13 divides n, and it gives you the shape and everything. Really nice. If 4 divides n, we have another pattern. If 4 divides n, then there exists an a, so that backwards e just means exists. And this a is going to be somewhere between 1 and n minus 1. So it could be 1, it could be 2, it could be anything, we don't know. Could even be n minus 1, n minus 5, who knows. But it's somewhere between 1 and n minus 1. Then a is going to have the structure 0. Let me make sure I get this right. A plus n over 4, n over 2. And then B will have the structure of, 0, A, n over 4, and A plus n over 2. Now, what that A is, we don't know. And there could be multiples of A that work. We're not sure. And that's another open problem, how to get that A without just guessing and checking. But we do at least have this kind of general formula. And if neither of those are true, if n isn't divisible by 4 or 13, then no such pairs exist. So otherwise, none. So that's pretty cool. And again, that's a result from physics, crystallography, shooting X-rays at crystals. So it's kind of neat that they figured this out. They figured this out in, like, I don't know, the 80s maybe, and it does have some applications in music, I suppose, especially microtonal music. All right, so that's homometry and the Z relation in, music sets and the cyclic groups in Zn. What if we wanted to generalize our idea of homometry to other things? Maybe rhythms. Are there homometric rhythms? Are there homometric chord progressions? So we're going to generalize the interval vector to other sets. Jack has a question. Jack says, for any n not divisible by 4 or 13, there's no homometric cycles. There are no homometric pairs that are 4 elements large. So this is just for 4 element sets. There could be 5 or 6 or 2 billion, but for 4 element sets, those are the only possibilities. Either those patterns or it doesn't exist. So Vin Luden says, what is homometry? Yeah, you probably missed the beginning. Homometric means that the two sets have the same interval vector. The interval vector is like all the intervals between all the notes in the chord, if that makes sense. So two sets have the same intervals, but they're not the same set. You can't transpose one to the other, that sort of thing. All right, so let's generalize our interval vector to a more general group setting. So what we're going to do is, first of all, instead of talking about 0, 1, 2, 3, etc., we're going to rewrite our group like this. So instead of 0, we're going to do it like multiplication. So let's say that 1 is equal to C, Z is equal to C sharp, Z squared is equal to D, Z cubed is equal to D sharp. You get the pattern, ... and then Z11 would be equal to B, and then, of course, Z12 is just going to be equal to 1 again. It's the same thing, really. It's just a new way of writing it. But writing our notes this way is actually going to be really helpful in a second, because we're kind of going to pull some polynomial stuff from your Algebra 1, your Algebra 2 classes. You remember foiling? Get ready to foil. All right. So in this case, an interval is going to be defined by multiplication and division. So let's say we had our major chord. Now it's going to be 1, Z to the 4th, and Z to the 7th. So what's the interval between E and G? Well, of course, the interval between E and G is a minor third, 3 semitones. But now we're not going to write it as 3, we're going to write it as z cubed. Does that make sense? Because if you think about it, z to the 4th times z to the cubed is z to the 7th. So everything's being reformulated in terms of multiplication here. And similarly, we're also kind of thinking about it in terms of division instead of subtraction. Z to the 7 divided by c to the 4th equals z cubed. All right, so we got that under our belt. So why are we doing this? Well, this gives us a really, really convenient way to redefine what the interval vector means. So let's say we want to find the interval vector of the major chord. What we're going to do is we're going to say 1 plus z to the 4th plus z to the 7th. So we're kind of turning our major chord into a polynomial here. And we're going to multiply it by a sort of inverse. So we're going to have 1 plus z to the negative 4, and you could also write z to the 8th here, plus z to the negative 7. And again, you could write, z to the 5th if you wanted. And if we were to FOIL this out and multiply this out, we would get a bigger polynomial that is exactly equal to our interval vector. So we would get 3 plus, I'm trying to remember what it was, z cubed plus z to the 4th plus z to the 5th plus z to the 7th plus z to the 8th plus z to the 9th. And that's kind of crazy, right? Just multiplying this out gives us our interval vector. But turning our idea of interval vector from something you have to count to do to just simple multiplication is going to really help us if we want to generalize it to rhythms and chord progressions. So is everybody okay with that? Yeah, we are multiplying by an inverse. I'm just trying to simplify it to like non-mathematician talk, if you get what I'm saying, Tom Z. Yeah. So, Tom Z, if you are familiar with mathematics, we're talking in terms of like group rings and group algebras. So we're turning our cyclic group into actually what we would call a group ring or group algebra. In this case, it would be R of Z12. So if that's helpful to you. We're taking elements which correspond to multisets of chords to elements in this group ring, and then multiplication, it's like an inner product. Since we have this inner product, it could be considered a group algebra. Multiplication gives us other elements in this set, which is kind of neat. All right. So Dio asks how that chord would sound, and I'll tell you it would sound terrible. Do not try to interpret the interval vector as a chord itself. That is incredibly not cool. It would probably sound terrible. All right, so with this new tool in hand, let's talk about chord progressions. So we need to first explain how we're going to rewrite chords in terms of polynomials. So for the math people in the room, we're going to be using the dihedral groups. So in this case, D24. So how we write an element of D24 is like this. We have R to some power, let's say I, times S to J. So in this case, I is going to be, less than or equal to 0, 11. And J is going to be between 0 and 1. So how this corresponds to chords is as follows. So let's say we had the chord E flat major. So E flat is 3 semitones up from C. So first we're going to write R cubed. So this first R part is just like the Z part earlier. It just tells us the root's position from C, if that makes sense. And then major or minor is going to be determined by S. So since it's major, we're going to write S to the 0. And of course, S to the 0 is just 1, because anything to the power of 0 is 1. So E flat major is going to be R cubed. As another example, let's say we had G minor. G minor would be R7. Again, G is 7 semitones up from C. times S to the 1, because it's minor, S1 is going to be minor. This is the same thing as R7S. So is everybody okay with this notation? Does that feel comfortable? So let's figure out how we do multiplication in this system. So if we're going to be multiplying polynomials of these guys, we got to know the rules. So let's say we were to multiply E flat major times G minor. So we would have R cubed times R7S. Well, we can just combine this. R cubed times R7 is R10 times S. Let's say we wanted to do it the other way. Now this is tricky because multiplying in the other direction does not give you the same answer. So now we have R7S R cubed. Now we can't just shift the R cubed over to the other side. That's not how this works. We're no longer dealing with commutative multiplication. So we need to invoke this new multiplication rule. If I have S, that was a terrible S. If I have S times R to some power, let's say N, this is equal to R to the negative N times S. So this is our new little multiplication rule. So let's apply this rule. We have R7 times SR cubed. If we apply this rule, this turns it into R7 times R to the negative 3 S. And again, R to the negative 3 is the same as R to the 9. And this is going to give us 7 minus 3 is 4. We get R4S. So we have two different results. Again, notice that. Multiplying left and multiplying right gives us different answers. Okay? Don't make that mistake. So if you wanted to interpret it, you can interpret it in terms of PLR groups. If you're familiar with Neo-Riemannian theory, you could also interpret it in terms of the TI group if you prefer that. At any rate, we're getting another number inside of our little space of chords. So here, think this result is like we're moving up four semitones, but then we're turning minor, right? So multiplication from the right can be thought of as like the TI group. Or sorry, that would be multiplication from the left is like the TI group. Multiplication from the right is a bit harder to interpret, but you can interpret it in terms of the PLR group. It's a little weird. I don't fully understand the correspondence, so I'm not going to explain it, but it's a thing. All right, so now the tour de force. Do there exist homometric chord progressions? So in other words, if we have a set of chords and another set of chords that aren't equal just by transposing it or inverting it, can we get homometry? The answer is yes. It's a little less clean. Let me find my examples because they're a little long. Yep, here they are. I'm not going to write this whole thing out, but here's an example. Let's say we had the chords S, R. I'm going to have to keep flipping back and forth because there's a lot of terms. Sorry, that's RS. R to the... my short-term memory is so bad. R to the 5th. R to the 5th S. And R to the 11. So again, if you wanted to interpret this in terms of chords, we have C minor, D flat, minor. So I'll put a little M for minor. This would be F major. This is F minor. And this would be B major. So that's if you wanted to interpret it in terms of chords, which you probably will. You're all musicians. And let's say our second set is 1, S, R4S, R5, and R5S and R6. So if we wanted to find the interval vectors for these guys, what would we do? Well, we would just turn it into a polynomial-ish, Again, it's not an actual polynomial, but it looks like a polynomial for the non-math people. We turn it into the polynomial and multiply it by its inverse. So I'm not actually going to do the foiling out because that would take forever. It did take forever when I did it because I am not good at high school algebra. But this is what it might look like. So we multiply this guy, and now we're going to take its inverse. So s to the negative 1 is actually just the same as s. So just leave it like that, because if you remember, we only have S0 and S1. If we had S2, that would just be looping us back to S0. Okay, so we have S. We have S R inverse. And again, we have to flip this. We have to flip these guys because this multiplication is not commutative. So when we're doing the inverse, we have to flip it around. So think about RS times SR inverse. First these middle guys cancel, then these outer guys cancel. So that's why we have to flip it. Then we would have, oh, come on, pen. R to the negative 5 plus SR to the negative 5 plus R to the negative 11. So for shorthand, let's just say that this set is A and this set is B. For shorthand, this really means like A times, I don't know, A bar. We'll call it A bar. So what this multiplication is going to give us is that multiplication will give us, let me just make sure I get it right because I always confuse them. That's left. Yeah, it is left. This is the left interval vector as their product. If we were to multiply it the other direction, this would give us right. So left IV, this guy would be right IV. And they will be different. Well, sometimes they'll be the same, but many times they will be different. So you have to distinguish left and right in this case. And you can do the same with B. And what we'll get for this example, at least, is that B has the same left and right. So, I don't know, let's say left B equals right B. And actually, these two guys are also going to equal left A. So that means left interval vector. However, the right interval vector for A is not equal to these guys. So that's interesting. That means that A is left homometric to B, since they have the same left interval vectors. However, they are not right homometric. So that's sort of interesting. And you can find examples of sets that are both left and right, or just left. But you do have to distinguish it. So I think that's a good example to show why you have to distinguish it. All right. Now let's think about, let's go with this result. So let's say we have two sets, A and B. First of all, you need to know that A double bar, so in other words, the inverse of A, is the same thing as just A. I think that makes sense. If you inverse and inverse, you get back to the same guy. But we have this interesting fact. Let's say A and B are left homometric. Okay? Then we know for certain that A bar, or A inverse, and B bar are right homometric. So that's kind of cool. And we could switch the left and right. You know, we could say if A and B are right homometric, we know that their bars are left homometric. And I do use a double arrow here because it is an if and only if statement. It is impossible, if you had their inverses were left homometric, it would guarantee that the normal version is right homometric and vice versa. So that's really cool. And that also tells us something neat. There are the same amount of left homometric pairs as there are right homometric pairs. So that's pretty convenient. And it also helps a lot in enumeration because if you were to just list all the left homometric sets, you would automatically get all the right ones for free just by inverting everything. So that's really convenient and cool, etc., etc. Let's see. All right, so now let's bring it back to the cyclic groups that I talked about at the beginning. So first let's define a projection. So we're going to call projection with pi. So let's say we have a musical or a set A of chords, right? So this is a dihedral group set. The projection of A is going to just be like taking it down to our Z12. So A is in D24, which means chords. The projection of A is going to be in the cyclic group, which is, again, think of it like notes. All right, so I don't know. I think it's easier to explain this just with an example. So let's say that we had A was S, I don't know, R4S, R6, and I don't know, maybe R9S. Then the way we're going to project this down to our sets is we're just going to ignore the S's. We're going to ignore the S parts. So now the projection of A is going to be 1. We can't use R now. We're going to use Z. What? I erased. Eraser. So we'll have 1, Z to the 4th, Z to the 6th, and Z to the 9th. Does that make sense? I think that projection is fairly intuitive. We're just kind of getting rid of the minor or major component. If we had, E flat major, the projection of it would just be E flat. We're kind of throwing out all the additional fluff. All right, so what do we want to do with these projections? Well, there's one really important theorem we have about these projections. So let me clear the canvas. Let's say that A and B are right homometric. So they're going to be right homometric. And it's important that I say right. This will not be true for left. Then we know that the projection of A and the projection of B are going to be homometric. And again, if you remember Z12 and all the cyclic groups, there's only, or I shouldn't say left, there's only one homometry because left and right are the same. Multiplying left and multiplying right gives you the same interval vector. So we'll just say homometric. So this is kind of important, right? Because this tells you if I had a way to list all of the chord progression homometries or the dihedral group homometries, I could just project it down into Z12 or Zn, and then I would get all of the cyclic group homometries for free. That's really cool. However, again, this does not work for left. So if I had A and B left homometric, their projections would not necessarily be homometric. I would have to take their inverses, which would give me right homometry. If you remember the previous theorem, we would take their inverses, which would be right homometric, and then project them down. Does that make sense? All right, and then there's one other important thing. We're talking about homometry really meaning non-trivial homometry, right? In other words, we couldn't just turn one set into another by transposing it or inverting it. However, the projections could be trivial. So let's say A and B are not trivial. So I'm going to write it like this. A is not congruent to B. Actually, they probably like to do the squiggly. So A and B are not equivalent by translation, transposition, inversion, whatever. However, this does not imply that pi of A and pi of B, these guys could be trivial. They could be equivalent. So that's important to keep in mind. You're going to get some redundancies. However, oh God, my handwriting. However, if A and B are equivalent, then we'll know that their projections are also equivalent. So this implication, so it does imply this way. If they're equivalent, then the projections are equivalent, but not the other way. You could have equivalent projections, but not equivalent, unprojections, I guess. Tomsy says, what is the cause of that disparity? What do you mean? It seems like an important result that A and B are right homometric implies the P of A and P of B are homometric, but we don't have the same result for left. That is true. The proof is somewhat long. Let me actually pull it up because I haven't looked at it in a while. Sorry, just give me 1 second because I would like to answer that question well. But it does have to do with the fact that I showed earlier. I don't know if you remember when I showed that example earlier with E flat major and G minor. So E flat major and G minor, if you remember, their right interval was nice and neat. Their right interval was just R4S. So this is right. Their left interval was R10S, which, I mean, if you just look at it, I think that has like no real obvious meaning in terms of just intervals, right? So this is left. It has no obvious meaning in terms of intervals. It's like the PLR group. It's all about voice leading and things that are close just by shifting one or two voices, right? So if you're familiar with Neo-Riemannian transformation theory and all that sort of thing in the tonnets, you'll know that Riemann would say that, I don't know, C major and E minor are very closely related because they're just changing one note, right? They're related just by one transform. In that case, it would be L, the L transform. In this case, when we're projecting, we want to have the sort of nice neatness that the right multiplication has, which is just the TI group, which stands for translation and inversion. So the interpretation in terms of the TI group is we're transposing by 4 units and then inverting once, right? So that's kind of why qualitatively right homometry lines up so nicely with projections, if that makes sense. Mathematically, I would have to reread the proof. It's been a while since I looked at it, so, but that's sort of the fuzzy idea. So Tomsy's typing for those watching the recording, so I'm waiting to see what he says. Yeah, it's called PLR, not PMR. Those groups are not really special mathematically. Both of them are isomorphic to the dihedral groups. However, their isomorphisms are different, right? So the TI group is isomorphic in the obvious way that you would think, whereas the PLR group's isomorphism is not as clear. So that's why the musical interpretation sort of lines up nicely.
Again, just to quickly butt in, the PLR group is related to the TI group, which is the main thing we're talking about with the transpositions.
Yeah.
Because it is, I'm just trying to make sure I don't mess this up, but the PLR group is, I believe it's the center of the TI group. So it is, if you take the TI group as a subset of the symmetric group, so you know this as the TI group as a subset of all permutations, then the PLR group is the center. It's the only one that it's the only group that is not isomorphic, commutative with it. And vice versa. They're centers of each other. They're both commutative with each other, and they're the only. I keep wanting to say the word interpolations, but that's not the word. The word for when
duals? I don't know.
They are duals of each other, but I mean they're duals of each other within the 12-element symmetric group, which means nothing to most of you, but that's Tomsy might get it since they seem to be Matsy. Anyway.
Yeah.
That's how they're related.
No,
It's
thank
really
you for
weird.
that input, because I actually did not know that. I haven't really looked into the PLR groups and the TI group very much. I've mostly just been focused with homometry kind of abstracted. But no, that's really helpful. Thank you. So unless there are any more questions about this, I want to give a couple passing remarks on how this could be extended to rhythm. I had expected to go a little bit more in depth with rhythm, but seeing our time, I'm probably going to have to cut it short. Maybe I'll make another rhythm lecture sometime. But here's how we'll think about rhythm, just as an introduction for everyone. We're going to use something called the time span group, okay? So time span group. And how this is going to work is, let's say we had, the real number line, okay? And think of this real number line as time, okay? So here's 0 seconds, here's 1 second, and we could have negative seconds. It doesn't really matter where we start. But just think of the real number line as all of time. So then if we had a musical note, maybe a quarter note is, let's say that a quarter note is this length. So we're shading in this interval from 0 to 1. And it's a closed interval for anybody who's curious. How we're going to write this is like an ordered pair. So the first element is going to be where we start, and the second element is the duration. Okay, so maybe that's kind of a bad example to see. Maybe we want to look at a half note from 1 to 3. So we shade in this interval, the closed interval from 1 to 3. This half note would be 1 as the first pair, that's where it starts, and 2 is the length. Does that sort of make sense? So in general, we have T, like the start time, and then D, the duration, if that makes sense. Oh, yeah, okay. Jack has left a comment. He says that the PLR group is the center of the TI group as a subset of the permutation group. So, all right. So this is the basis for the time span group, and this is how we're going to talk about rhythms. A rhythm is just a set of all of these little time span elements, right? So how is multiplication going to work in the time span group? So how we're going to define it is this. Let's say we have two elements. Let's say T and delta. They like to use delta usually. And U comma capital delta. All right. So the multiplication will work thusly. We're going to have T plus U delta, and this is their product, so I'll put a little time symbol in there. So T plus U delta is the first element, and then delta is the second element, just multiplying those guys. So as a concrete example, maybe we want to multiply the two notes we'd had earlier. So we had 0, 1, and we had 1, 2. Again, that's a quarter note starting at 0 and a half note starting at 1, if you want to interpret it like that. Their product is going to be, well, T is just 0, so 0 plus U times delta is 1. And then multiplying their durations gives 2. So that's kind of neat. 1, 2 is what we get out. And that's what we should get out, because this guy right here, 0, 1 is the identity of our group. All right, so now that we have the actual, the multiplication written down, what are we going to do with it? So, sorry, let me just glance at my notes one more time. Uh-oh, I accidentally closed a tab. Give me a second, I'm sorry. Oh, come on. Here it is. I'm gonna copy paste an image of a rhythm, because I am really not great at drawing notes, and it would also probably take me a long time to write it all down. So I'm gonna just take a screenshot and see if I can post it in here. Hopefully I can just paste it in my little app. There it is. Hey, it worked. All right, can you guys see that rhythm? I don't know, say yes or something. I don't know. To answer your question, Tomsy, I'm pretty sure they weren't defined that way. I think that they just came up as a result of music theorizing, and it just kind of happens that they have that nice property. At least I'm pretty sure that's the order of operations, because those groups have existed since the 1850s probably, and this sort of, rigorous mathematical treatment of music theory hasn't been a thing until pretty modern times, I would say. So anyway, we have two rhythms, and we could interpret these as, sets. So maybe the first rhythm is 0, 1, since let's say quarter note is 1 beat long. I don't know, let's say this next guy is 1, 1, because it's starting at 1. Then we have 2, 1/2, and you get the picture. We could go on and on. But it's kind of funny what's so special about these groups. So what's special about these groups is that they are right homometric. So in other words, again, if you took those guys with their inverses and you multiply them, you'd get a sort of interval vector. And they have the same right interval vector, but not the same left interval vector. And what's interesting is nobody has found a simultaneous left and right homometric rhythm. So the open question is, are left and right homometry in this time span group mutually exclusive? And so that's a pretty interesting open question. It's one that I'm taking some look in. Maybe I'll figure something out. I don't know. Probably not. But that's kind of neat. So maybe the question you guys are having, and I should have explained this faster, is why did we define multiplication in this way? So the reason we define multiplication like this is because it has a couple really convenient properties. The first one is that elongating this rhythm preserves the interval vector, or I should say preserves intervals, preserves multiplication, whatever you want to say. So if we change the tempo, maybe this guy was originally quarter equals 90, and maybe we changed it to quarter note equals 60. And so we had to adjust the durations, and we had to adjust the starting spaces. That wouldn't change the interval vector. So we can actually think of transposition in terms of duration stretching. We're, dilating it or contracting the rhythm in terms of time. That's kind of neat. So that's how, I guess, if we were acting on some guy, let's say this was our element, and we were acting on it from the right with a transformation, U delta. So pretend the second guy is the transformation. This delta is stretching it, right? So that delta is, one equivalence relation, I guess, and it's going to preserve interval vectors. And similarly, this guy's U is just changing the starting position, right? If you look at the multiplication, that's all it's doing is shifting the starting position. And we would hope that the interval vector is preserved by just shifting the whole rhythm left to right in time. So that's kind of why we define multiplication like this. Now, preserving those two properties is really nice. However, it doesn't preserve something else. We have to lose something. And here's what we lose. So let's say we have two rhythms that are homometric like this, or I don't know, even equivalent, we could say. Multiplying them or acting on them by another element of the time span group is not always going to preserve order. So if we had, I'm trying to think of an example. Let's say we had one rhythm that was like, thinking about it on the number line, maybe we have one rhythm that's like this interval and these two tiny intervals, and maybe we have another guy over here that is this interval, and maybe there's a tiny interval here and a tiny interval here. Unfortunately, acting on these two guys isn't going to put them in the same, isn't going to preserve their time dependence, I guess I could say. So, for example, let's say we were acting on this big interval here by the element 1, 2. Okay? So what this would happen to this big interval is it's going to shift 1 unit to the right. Let me clear this up a little bit, actually. So let's say we have interval guy, big interval guy here. It's going to shift 1 unit to the right, so its image is going to shift a little like this, and it's also going to expand by 2. Now, when I say move 1 unit to the right, remember that the multiplication is t plus u delta. So 1 unit doesn't just mean 1, it means 1 duration of the original note. So it's going to shift to here and get twice as long. Does that make sense? Now let's say that we had, actually let's make it shift 2 to the right. I changed my mind. Let's say we're acting on it by 2, 2. So this big interval is going to be shifted 2, and it's also going to get twice as long. Does that make sense? Now let's say we have another small interval right here and act on it by the same element. So now again we're going to shift it 2 to the right and make it twice as long, but now that tiny interval just gets moved to here. You see the issue. We haven't preserved the order. We haven't preserved time. Now our shorter interval has been moved to the left of the bigger interval. That's kind of an issue. And, let's say that we made this shorter interval longer. Let's say it was like that instead. Its image would kind of completely change, right? Because now when we're shifting it over 2 intervals, it's going to be moving, we have 2 hops. So now it's going to be moving here. And so now we have preserved order, but now it's kind of smushed in there, and it's a whole mess. So there are limitations to thinking about rhythms in this way, but the advantages are, again, the interval vector is preserved by tempo and shifting left and right in time. So that's kind of all I want to say about rhythm, just because of time. Rhythm does get into a lot of Fourier transform stuff, like the discrete Fourier transform, and there's a lot of interesting things there that I could go into. I'll probably maybe make another lecture. I don't know. There might not be enough content. But at least you have one interesting result. Like I said, we don't know of any left or right simultaneous left and right homometric rhythms in the time span group. And it seems like there aren't any. So that's kind of neat. So I think that's where I'm going to end it for today. If there are any questions, put them in the chat. I'm at this point probably going to stop the recording unless there was a question. Okay, so Tom Z asks what my background is and why I give free lectures. So I'm a math student. I'm currently a sophomore working on my pure math degree. But I do have a pretty large interest in music. I've been doing music for a while, and I've had the server for a while as well, So I like to try to incorporate math into music theory and expose people to some interesting intersections between the two, because there really is a lot of overlap between math and music theory, and I think it helps people if they can analyze music more numerically and abstractly, and there's a lot of cool stuff that goes into that. So I just kind of give free lectures because I think they're fun, and I like teaching people things. Jack is typing. Hello, F major 7. Jack asks, you need the rhythm to be quantized before you can talk about homometry at all, right? You mean like quantized to like the rationals or something? Or the dyadics? Actually, no. The time span group works with any rational numbers, though I would imagine that it's probably difficult to find homometric groups that are, irrational multiples of each other or something like that. I don't know if they've found any like irrational rhythms. Maybe they don't exist. Maybe that's another open question. But I don't see any reason why you'd have to quantize it. Other than, it's just probably hard to find examples. Yeah, I mean, the time span group is, you just had, the t can be any real numbers. So, t is an r, and your duration just has to be a positive. So, duration guys in the positive reals. Or probably not 0. I mean, I guess you could have 0, but I don't know why you would. That's stupid. But yeah, good question. Any other questions? Otherwise, I think I'll probably end it here.